So let me go now to this, what's called an n surface problem. N is an unknown number, right? N surface problem. And then we'll see how the equations develop, and then you can actually use them from that point. So our n surface problem is happens to be a 4 surface problem. What I want to do to start is just show you that with this type of problem, it doesn't really help to draw out a resistance network. All right, so let's take our nodal approach. Let's call this surface 1 and 2 and 3 and 4, and say I've got EB1, EB2, EB3, EB4. So now I have to capture all the geometric resistances, or spatial, is also called spatial resistance. To capture those resistances, I'd have to do that between every possible node. And I have to compute view factors between every possible node. So that would look something like this, right? 1 here, 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 here. I also now have a resistance from 4 to 2. I also have a resistance from 1 to 3. Okay, every possible combination. Now if you go to like 5 nodes or 6 nodes, you can see it becomes a problem. If you try to write this network out in like a meaningful way, or write out like a parallel flow heat transfer problem, something like that, it's hard. It doesn't really work very well. You very quickly become like disoriented in trying to solve the problem. So what we want to do is come up with like a system that's going to work in general. And so to do that, we develop the following system of equations. This is generally the approach that I would recommend for any problem that involves more than like 2 surfaces or 3 surfaces. So really any problem that is practical, that you really care about. So what you want to do is you're going to say the heat transfer rate, Q dot, across surface I. Right, so this is like if I were to draw a heat transfer rate like this. So this would be Q dot 1. That's the heat transfer rate across that surface, entering into the radiation problem. It is not from like I to, or like from 1 to 2 or from 1 to 3. Those are different. Right? This is just across the surface. So Q dot I is going to be equal to the summation for the index j. So we're going to take j from 1 up to n. So n in this case is 4, right? 4 surfaces. And I'm going to sum basically all the energy equations. So AI, Fij, sigma, Ti to the 4th minus Tj to the 4th. I'm going to do that for all I in the set from 1 to n. Okay, in other words, let's just write this in terms of emissive power. So Q dot I summation j equals 1 to n of AI Fij, EBI minus EBJ. Again, for all in the set, for all I, clear that up, for all I in the set from 1 to n. So notation, right? Notation is important here. I am summing over the index j. That is like, I take all the variants of this equation that involve Fi to j, so Fi to 1, Fi to 2, Fi to 3, Fi to 4. And then I take EBI to EBJ, 1, 2, 3, and 4. So in a 4-surface problem, I'm going to have 4 terms I'm summing together for this one Q dot, right? Or n in the general case. And then I repeat that for however many surfaces I have. So in this case, I'd have I equals 1, 2, 3, and 4. So I'm going to have 4 different Q dot equations, 1 for each surface, each of which contain 4 terms in them. All right? So that's what the notation is really important here to get that right. But so now you have, oh, yeah, question.
Is that Q dot coming from like outside the system?
Yeah, it's like a net heat transfer across the surface. Yep.
So this makes me sound like a total heat that's coming from, let's say, for example, node 1, like a donut going into 1, is split across all from surface 1 to all the other surfaces. Is that what this is basically saying?
Yes, exactly right. So the comment was, this is saying that Q dot 1, for example, this is expressing the heat transfer from one to all other surfaces together. Yeah, that's right. Okay, so what this gives you is now a system of equations, right? You repeat this n times, you have n equations. So coming out of this, we have n equations. This whole thing gives us n equations. Is that enough? Well, what do we not know? We don't know the following. I guess we don't know EB, I, right? So the emissive power of whatever surface, that's n. We have n of these. What else don't we know? We don't know Q dots, right? We don't know Q dot I. So together, these give us 2 times n unknowns. So I guess we're halfway there, right? So you develop this system of equations, this multi-surface problem. You apply the energy balance as shown here. The summation equation gives you n equations. That's halfway. Well, what's the other half? Well, unfortunately, there's not like an easy answer, but it's basically that you have to enforce like boundary conditions. All right, and that means for every surface, every one of your n surfaces, you have to decide something that you know about it. Either you know the heat transfer rate, or you know the temperature, or there's some other equation that you can apply that helps you solve for things. But basically, you have to go through and one by one, specify something else about the problem. All right? So I think the best way to maybe illustrate this is through an example. So what I want to do is first, I'll talk through the different boundary condition types that you can enforce, and we'll do this hopefully quick example. All right, so the boundary condition types, like I said, you need, we need n additional equations. So there's basically 3. So 1, 2, and 3. There's basically 3 boundary condition types. One is a known temperature. Okay, so if we know our temperature, then that says we can take sigma T to the 4th, and that will then give us EB, the emissive power of that node, the potential that we care about. The second thing is just known emissive power. This is, directly knowing EB. Under which circumstances would you directly know EB and not the temperature? None, I guess. But theoretically, you could do this if you really wanted to, or you had somebody who was writing a homework and was kind of lazy and just gave that to you. But this is the second one that you could probably use. Okay. The third one is a known surface heat transfer rate. That would be the Q dot at the surface. Okay, so with those 3 things, we can go through the example, and then you'll kind of see like where we need to introduce this stuff.